So it's still 5.1, and we're looking at example 3. Part A says, write the chemical equation for the dissociation or autoionization of water and the expression for the equilibrium constant or ion product constant, Kw. Take this one step at a time. First, write the chemical equation for the dissociation of water or the autoionization. So here's the reaction we're talking about. Here's liquid water, and this is a reversible process. And just in its natural state, some of the water breaks apart into hydrogen ions and hydroxide ions. Any sample of water that we have, this is constantly going on, constantly going back and forth. Some of the water is splitting up, some of these ions are recombining into water. You could write it another way, and you'll see this sometimes based on a different ion. H2O. The alternative to H plus, and this is more or less the same thing, but written differently. This is a polyatomic ion. Remember its name? It's hydronium. So hydronium and hydrogen ion really indicate the same thing. And in a sample of any water or any acid, 100% of the time, these are interchangeable terms. And we need a 2 here. So this is the dissociation of water. Breaks apart into hydrogen and hydroxide. So we want to write an equilibrium expression for this, and we call it Kw. And if you think about equilibrium expressions, it was always the concentration of the products on top. So that's the concentration of hydrogen times the concentration of hydroxide. And remember, they would have exponents. The exponents are based on the coefficients, which are 1, and so our exponents are 1. Now, don't write this part down, because I just want to talk about it. It would be over the concentration of the reactants, but it would be really weird to put over the concentration of water, because what's the concentration of water? It's silly, right? This would be a huge number compared to these, and so this would completely ruin all of our calculations. So with this liquid water, we leave it out. Just like solid would stay out of my equilibrium equation, the liquid water stays out of here. So let me get rid of this. And this is an AP formula that is on your sheet. Kw, the dissociation product of water, equals hydrogen concentration times hydroxide concentration. Or based on the second one, remember hydrogen and hydronium are interchangeable. This is your other possibility. Part B, if it's not stated, we assume the solution is at 25 degrees Celsius. At 25 degrees Celsius, and the Kw, the dissociation product of water, is always the same number, 1 times 10 to the negative 14. It says, however, at 100 degrees Celsius, the Kw of water is 5.13 times 10 to the negative 13th. And so this just gives you an indication that the number changes with temperature. It says, is the dissociation of water endothermic or exothermic? I'm not sure to what degree we need to know that. Let's just put endothermic. And the reasoning behind it, as temperature increases, kW increases, and that means this reaction is going to favor the products. So the hotter it gets, the bigger this K value gets, and the more it's going to favor the ions instead of just the liquid water. Something that we mentioned yesterday down here at the bottom, for the pH scale, which is really our standard measurement for acid or base. It's on a 1 to 14 scale. 1 to 7 is acidic, 7 to 14 is basic, exactly 7 is neutral. It's neither one. And again, this is at our 25 degrees, which we pretty much always deal with 25 degrees, except for this next example. I'm just going to show what happens at a different temperature. So it says, what are the pH, pOH, hydrogen concentration, and hydroxide concentration of a neutral solution at 100 degrees Celsius? So here's a note: in pure water, so these two things are related. Neutral meaning pure water. Hydrogen concentration and hydroxide concentrations are equal. So in this particular situation, using the same expression, Kw equals concentration of hydrogen times concentration of hydroxide. The only thing that really changes is we have a new value for Kw, which they just told us a couple lines above. 5.13 times 10 to the minus 13th. And we want to know what this concentration is. They're the same, so you could call this one X, you could call this one X. X times X is X squared. And so in order to find X, we're going to take the square root of that number. Put it in scientific notation, 7.16 times 10 to the minus 7. And so this is the hydrogen concentration. This is the hydroxide concentration. These are in terms of molar. Excuse me. So to find the pH and the pOH, we're going to use the formulas from our AP sheet. So the pH is negative log of the hydrogen ion concentration, which is 7.16 times 10 to the minus 7. Let's pause before we put this in your calculator. Let's try a rough estimate of the pH. Remember, it's going to be something around the exponent. So maybe something around 7. But this is getting pretty big. This is almost 1 times 10 to the negative 6th. And so somewhere between 6 and 7 as an estimate. Makes sense? Now we can put it in our calculator. Negative log answer. And we come up with 6.14. And that agrees with our rough estimate. And the multiple choice sections on the AP exam will make you estimate the pH based on that. So that's something you're going to want to remember how to do. There's an AP formula that says 14 equals the pOH plus the pH. That's not going to work in this situation because this only works at 25 degrees Celsius. So we're not going to do that. But we don't really have to do any work because the negative log of H plus is the same as the negative log of the OH minus here. No, don't even waste time in our calculator. These two numbers are the same. And so 6.14 is your cutoff between an acid and a base in this solution at 100 degrees Celsius. So let's write that last thing. At 100 degrees Celsius, pH of less than 6.13 is acidic. pH of greater than 6.13 is basic. And exactly 6. I'm at 1.4, not 1.3. There we go, fix that. And exactly 6.14 would be neutral. This is just to show that it does change with temperature. This is not a number that you should memorize. Just understand what we did here. Part D says, what is the pH, pOH, hydrogen concentration, hydroxide concentration of the solution in example 1? So we're looking for these same things again. So looking back up at example 1, we know a couple of things. Concentration of potassium hydroxide is 0.00015 molar. Which means my concentration of hydroxide is, anybody? 0.00015 molar. Same number.
Didn't we already do these values in example 1?
Yeah, that's what I was just looking at. Why it's. I forget where you got this number. Yeah, this looks like a complete repeat. Let's scrap this. I'm not sure why he's making us repeat this. Yeah, let's move on. Okay, so on the next page, we have definitions of acids and bases, and this is something that came up in your textbook reading yesterday. Hopefully you're looking over the material. Remember, speed reading, don't try to absorb every detail at once. You want to make it through quickly. If you speed read it, you could do it twice or 3 times in the amount of time that it takes you to try to absorb every detail on the first try. So probably a change in our reading strategy. There's Arrhenius. So the Arrhenius acid, what happens is it directly increases the hydrogen ion concentration by dissolving and adding hydrogen to the solution. So your examples are things like HCl, hydrochloric acid. You put it in there, it dissolves, now there's more hydrogen ions. Same thing with nitric acid, HC2H3O2. What's this thing called? How about let's cover this up for a second. What's this called? Acetate. Good. So that's the acetate ion. So let's come back over here. Any guesses as to the name of this acid? We haven't gone over acid names yet, but basically we're going to take the name of the ion and replace the ate or the ite with an ic, sometimes OUS, whatever. But this is acetic acid. So acetate makes acetic acid. Same idea. This one is nitrate, so it's nitric acid. The Arrhenius base, it directly increases the hydroxide concentration. It adds hydroxide to the solution. So your examples are things like KOH, potassium hydroxide, NaOH, sodium hydroxide, or there's one, calcium hydroxide. Bases have no special names. We just use their regular names. Arrhenius acids are really the simplest. The next one you have are called Bronsted-Lowry. And this O has this weird little dash through it. I'm not sure how you pronounce it. So it's based on not necessarily is it adding hydrogen ions to the solution or is it adding hydroxide ions. It has to do with protons. Is something giving away protons or is something picking up protons? And so the Bronsted-Lowry acid is what we call a hydrogen ion donor. And if you think about a hydrogen ion, it's pretty much the same thing as a single proton. Because most hydrogens don't have any neutrons, so the nucleus is just one proton. And if it lost its electron, then it's just one proton. And the base, rather than being hydroxide, it's still related to this hydrogen. It's something that will accept this proton. There's a term here, amphiprotic or amphoteric. And this is a substance that can donate and accept these protons. This is a substance that can act as the acid, or it can act as the base. It's capable of doing either one. Best example, water. Water can give away a proton, it can accept a proton. Meaning it can end up as hydroxide or it can end up as hydronium. So amphiprotic or amphoteric. I'm not sure that AP favors one of these words over the other, so you might understand both. Here's something to write down, a note. Under the Bronsted-Lowry definition, many bases are not ionic hydroxides, meaning that there's no OH in the chemical formula. A good example of this is ammonia. When you dissolve ammonia in water, it becomes NH4+, meaning it accepted a hydrogen ion, and that makes it a Bronsted-Lowry base. Example 4, write the equation for the neutralization process that produces the salt calcium phosphate. Here's the basic of what happens. An acid plus a base has two products, water and a salt. Written a different way, this is a lot of the times how you'll see it. HA, hydrogen and its anion, plus the base, BOH, yields, here's H2O, and the salt, Ba. So we're looking for a reaction that produces the salt calcium phosphate. And real quick, what's the charge of calcium? So quick review, it's in group 2A. Everything in group 2A has this charge. And then phosphate. Does anybody know what phosphate is? Formula and charge.
3 minus.
The charge?
PO4 3 minus.
3 minus. Phosphate. So PO4 3 minus, which means the formula for this thing that we're looking for, this particular salt. Here's my H2O, and here is calcium 3 and PO4 2. So we just have to figure out the two things that make it. Now you see this calcium, that's my B. And so this is going to be calcium hydroxide. Keeping in mind the charges, it's CaOH2. Same reason as this. Here's the calcium, here's the hydroxide. It takes 2 of these to equal 1 of these. And over here I have my hydrogens and my PO4s. And in order to even out this -3 charge, we have to have 3 of these positively charged hydrogens. So if you know one of the products, specifically the salt, you could work backwards and figure it out. Want to take a crack at the name here? Anybody?
I'll pass.
Remember we had acetate, became acetic acid.
Phosphoric acid?
Phosphoric acid. Yep. Or you might call it phosphoric acid. It's one of those weird ones where they stick the OR back on. But yeah. So that's example 4. Let's finish 5 and 6 there quick. Example 5, write the proton transfer equation for the process when solutions of acetic acid and ammonia are combined. Identify the acid base, conjugate acid, and conjugate base in the process. So acetic acid is hydrogen with the acetate ion. They both have charges of 1. There it is. Does anybody happen to remember the second formula for acetate? It looks like this. CH3COO minus. Let me tell you something about the AP chemistry exam. They like to use this one, and I'll show you why. Instead of writing acetic acid like this, I'll write it down here. CH3COOH. And what does it look like to you? We might be tempted to say, here's a hydroxide, it's a base. And so anytime they talk about acetic acid, it's this. Because they want to see if you really know your stuff versus you only know Chem 1 level stuff. So this is their version of acetic acid. You might think about that. I'll probably mention that another 50 times before we take the test. Plus, our base is NH3. So let's identify these ahead of time. Acetic acid is the acid. Aside from the obvious, the name, it's got that hydrogen that's going to give away, which leaves us with acetate. And this hydrogen is going to come over and it's going to join with this NH3, producing NH4 plus. That's ammonium. And that's why NH3 can be a base, because it is accepting that proton. So you look at how are these things related? We have acetate or acetic acid and acetate. That's their connection. The hydrogen is not the connection. The rest of it is. Acetic acid to acetate. These are what they call a conjugate acid-base pair. So this is the acid. This is what we call its conjugate base. This means it could act as a base. If you put in a bunch of hydrogens, this one might pick up a hydrogen because it's looking for a hydrogen. So, but those are a conjugate acid-base pair. And my other pair is ammonia, ammonium. They're related by the basic compound, not that one proton. So ammonia is the base, NH4 plus, which now has really one too many protons. It could behave as an acid given the chance, and so we call that the conjugate acid. Example 5 says write the dissociation, example 6, write the dissociation reactions for these two things. So this is my acetic acid plus water, a reversible process. We end up with, let's put the hydronium first. Hydronium plus that acetate. And these two would be a pair based on the water. These two would be a pair based on the acetate. Same thing for the ammonia plus the water. This reversible process will create hydroxide. There we go. And NH4 plus. That's